Today we'll discuss RLC circuit in series and mathematics behind it. We are going to consider three cases. First one is natural response. Second, RLC circuit in series with a DC source. And third, RLC circuit in series with an AC source. First, we'll dive into the concepts of mathematics that we'll need to solve questions in RLC circuit. The first thing we need to know is how to solve a second order homogeneous differential equation. So a second degree homogeneous equation with constant coefficients is given by d2y upon dx square plus a dy by dx plus b y equals to 0. At times this equation is written as y double dash plus ay dash plus by equals to 0, or there is another way of writing it, which is in terms of operator d. We write this as d square plus ad plus b y equals to 0. So any differential equation of this form is a second order linear homogeneous differential equation. Now how do we solve this? Now we know that for a linear homogeneous second degree equation, solution is of the form y equals e to the power lambda x. So if we write y dash, there will be lambda e to the power lambda x, and y double dash will be lambda square e to the power lambda x. So what we'll do is we'll replace these in this equation. So we can write lambda square plus a lambda plus b into e to the power lambda x equals to 0. So from here we'll get a quadratic equation which is lambda square plus a lambda plus b equals to 0, and we call this equation as characteristic equation. So the first step is to write characteristic equation. It's a very simple step, and we can do it just by looking at the differential equation. Say for example, suppose I say equation is y double dash plus 2y dash minus 3y equals to 0. I can directly write its characteristic equation as lambda square plus 2 lambda minus 3 equals to 0. So from this second order linear homogeneous differential equation, we have to form a characteristic equation which is basically a quadratic equation. Now once we have this quadratic equation, lambda square plus a lambda plus b equals to 0, we know for a quadratic we have three possibilities. First possibility is when d is greater than 0, that is roots are real and distinct. Second possibility is when d is 0, that is when roots are real and equal. And third possibility is when d is less than 0, that is when the roots are imaginary. Now if the roots are real and distinct, and suppose we have two distinct roots, lambda 1 and lambda 2, then solution to this differential equation, it is given by y equals c1 e to the power lambda 1x plus c2 e to the power lambda 2x. Now if the roots are real and equal, in that case lambda 1 is equal to lambda 2, and suppose it is equal to lambda, then in that case solution to this differential equation, it is written as y equals c1 plus x c2 e to the power lambda x. And then we have our third case when the roots are imaginary. The roots, they'll be of the form sum alpha plus minus iota beta. In that case solution to this differential equation is given by y equals e to the power alpha x c1 cos beta plus c2 sine beta. Right now, we'll not bother about how do we get these solutions. And if you are really curious, I've discussed the solution to these three cases in one of my previous videos. I'll provide the link to that video in the description below so you can see for yourself how do we arrive at these three solutions for three different cases. Now, let us take up an example. Say, for example, we need to solve this differential equation d square y upon dx square minus 4 dy by dx plus 3y equals to 0. Now we can write its characteristic equation as lambda square minus 4 lambda plus 3 equals to 0. Now this is lambda minus 1, lambda minus 3 equals to 0. So we have two distinct values of lambda, lambda equals 1 and lambda equals to 3. So we can write its solution as y equals c1 e to the power lambda 1x. So there will be e to the power x plus c2 e to the power 3x. So the solution of this differential equation is y equals c1 e to the power x plus c2 e to the power 3x. Let's take example for the second case. Suppose equation is d2y upon dx square plus 4 dy by dx plus 4y equals to 0. Now characteristic equation will be lambda square plus 4 lambda plus 4 equals to 0. So we can write lambda plus 2 whole square equals to 0. So we'll have both the values as minus 2, and if both the values are same, we can write its solution as y equals c1 plus x c2 e to the power lambda x, which is e to the power minus 2x. So the solution of the second differential equation is y equals c1 plus x c2 e to the power minus 2x. Let's take another example. Say, for example, equation is d2y by dx square plus 2 dy by dx plus 5 equals to 0. Its characteristic equation will be lambda square plus 2 lambda plus 5 equals to 0. Now this is lambda plus 1 whole square equals minus 4, or lambda is minus 1 plus minus 2 iota. Now here alpha is minus 1 and beta is 2. So its solution will be y equals e to the power alpha x, and alpha is minus 1. So there will be e to the power minus x, and then c1 beta is 2 cos 2x plus c2 sin 2x. So this is how we solve a second order linear differential equation which is homogeneous and having constant coefficients. And if you recall simple harmonic motion in SHM, you solve this equation which is d square x upon dt square plus omega square x equals to 0. Now this again is a second order linear differential equation with constant coefficients and omega is positive. So if we write its characteristic equation, we can write lambda square plus omega square equals to 0, or lambda will be plus or minus iota omega. Now here alpha is 0 and beta is omega. So solution to this differential equation will be x equals c1 cos omega t plus c2 sin omega t. And depending on the initial condition, you get the value of amplitude and phase, which we generally express as a sine or cos omega t plus phi. So now we know how to solve such second order differential equations. Now for natural response, As well as if you want to solve for current in a DC circuit, you'll just need to solve homogeneous linear differential equation. But if you want to solve it for charge or for voltage, or if you have an AC source, then this second order differential equation, it will not be a homogeneous linear differential equation, but it will be a non-homogeneous linear differential equation with constant coefficients. So in those cases, our differential equation will be of the form d2y upon dx square plus a dy by dx plus by, and this is equal to some Rx, or R is a function of x. Now solution to this case is given by y as a function of x. It is written as yhx plus ypx, where this yhx is solution of homogeneous equation, which we know how to solve, and this ypx is called as particular solution. So here the first step would be to find yhx, and for that all you need to do is you need to solve this homogeneous differential equation d2y upon dx square plus a dy by dx plus by equals to 0, which will give you lambda square plus a lambda plus b equals to 0. And now we know how to find solution to this differential equation, and we'll say this solution is yhx. Now the second step is to find its particular solution. Now in order to find its particular solution, there are few methods, and one of them is method of undetermined coefficients. Now in method of undetermined coefficients, there are certain functions for which we already know the choice of yp. In our case, that is for RLC circuit, this response function Rx, or this driving force Rx, will either be some constant C or it will be some sinusoidal function, say E naught sin omega t or E naught cos omega t. If Rx is constant, then shortcut is we'll take this yp as some constant k, and if Rx is either of E naught sin omega t or E naught cos omega t, we'll take this yp as a sin omega t plus b cos omega t. Now yp is a solution to this differential equation. So what we'll do is we'll find y dash p, we'll find y double dash p, and we'll put it in this equation. So we'll get d square yp upon dx square plus a dyp upon dx plus byp, and this is equal to Rx. From here, you'll get the value of these constants k or a, b. So after this step, you'll also have this ypx. So now we can write solution to this differential equation. So solution to this differential equation yx will be this yhx plus ypx. Now let us take up an example. We are given this differential equation, which is y double dash minus 4y dash plus 3y, and this is equal to 1. So now this is no longer a homogeneous linear differential equation. So what we'll first do is we'll find yh, and for this we'll write characteristic equation for this homogeneous part. So it'll be this lambda square minus 4 lambda plus 3 equals to 0. So we'll get lambda is 1 and lambda is 3. So we can write this YHX as C1 e to the power x plus C2 e to the power, and lambda 2 is 3. So it will be e to the power 3x. So that's the solution of your homogeneous part. Now we need to write Yp. Now in this case, R is constant, and we know that when R is constant, then we let Yp as some constant k. Now y dash p is 0, y double dash p is also 0. Now we'll put these values in this equation. So it will be 0 minus 0 plus 3k equals 1. So value of k is 1 by 3. So your particular solution, it is nothing but 1 by 3. And once we have Yp and Yh, we can write solution to this differential equation. So solution to this differential equation Yx will be given by C1 e to the power x plus C2 e to the power 3x plus 1 by 3. So this is how we solve non-homogeneous second order linear differential equation with constant coefficients. Now we'll come to solving RLC circuits. Now the first case that you want to consider is natural response. So in this RLC circuit, there is no external voltage. We'll define the initial conditions. So at t equals 0 negative, the switch is open. There is no current in the circuit. And this capacitor, it is charged, and voltage across capacitor is V0. So this capacitor, it is charged, and voltage across this capacitor is V0. And suppose this is plus and this is minus. Now when the switch is closed at t equals to 0, the current, it is going to flow in the circuit. Now suppose the current flowing through the circuit is I. Now using Kirchhoff's law, we can write L di by dt plus IR, and voltage across capacitor is Q by C, and this is equal to 0. Now we differentiate it again. We can write L d square I by dt square plus R di by dt plus dq by dt, which is rate of flow of charge, and it is nothing but current. So there will be I upon C equals to 0. So we can write d square I upon dt square plus R by L di by dt plus I upon LC equals 0. Now what we'll do is we'll let some alpha, and this alpha is R upon 2L, and we'll write some omega naught square, and this is 1 upon LC. Basically these two terms, alpha and omega naught square, they have physical significance. This alpha, it is called as damping coefficient. And this omega naught, it is called as resonant frequency. We can write this equation as I double dash plus 2 alpha I dash plus omega naught square equals to 0, and this is nothing but a second degree homogeneous linear differential equation. Now we know how to solve it. So all we need to do is we need to write its characteristic equation, and there will be lambda square plus 2 alpha lambda plus omega naught square equals to 0. So from here we can write lambda equals minus 2 alpha plus minus under root of 4 alpha square minus 4 omega naught square upon 2, which is minus alpha plus minus under root of alpha square minus omega naught square. Now since this is a quadratic equation, we'll again have three cases. So for this RLC circuit, we'll have three conditions, and the first condition is condition of overdamping. We'll have the condition of overdamping when discriminant is greater than 0. That is, when alpha is greater than omega naught. And we know that alpha is r upon 2l and omega is 1 upon LC. So we can also write when r is greater than twice under root L upon C. Now in this case, we'll have two distinct roots. Lambda 1, which is minus alpha plus under root of alpha square minus omega naught square, and lambda 2, which is minus alpha minus under root of alpha square minus omega naught square. So in this case, this IT will be given by this C1 e to the power lambda 1 t. So there will be e to the power minus alpha minus under root of alpha minus omega naught square t plus C2 e to the power minus alpha plus under root of alpha square minus omega naught square into t. So when the switch is closed, this is the transient response of the circuit. Now using initial conditions, we can find the value of C1 and C2. Now we know that at t equals 0 positive, now there will be no current in the circuit. So basically this I will be 0. So there will be no current just after t equals 0. Now this capacitor is going to work as a DC source, and with no current, all the voltage drop is going to go across the inductor. So in that case, voltage across inductor will be equal to V0, which is initial voltage in the capacitor, and this is equal to L di by dt. So we can use initial values. So if we put t as 0, I is 0, so we'll get C1 plus C2, and if we differentiate this, we can find di by dt, or we'll find L di by dt at t equals to 0. So there will be L, and di by dt will be C1 exponential function, its derivative will be minus alpha minus under root of alpha square minus omega naught square into e to the power 0 is 1, and plus C2, and again its derivative, so there will be minus C2 alpha plus under root of alpha square minus omega naught square, and this is equal to V0. Now we can rewrite this as minus alpha C1 plus C2 and plus under root of alpha square minus omega naught square C1 minus C2, and it will be equal to V0 by L. Now we already know C1 plus C2 is 0. So from here we'll get the second condition that C1 minus C2 will be V0 upon L under root of alpha square minus omega naught square. Now if we add them, we'll get C1, and if we subtract them, we'll get C2. So from here we can write current in the circuit as a function of time. Now we'll come to the second case, which is critical damping. Now in critical damping, basically D is equal to 0. That means alpha, it is equal to omega naught, or we can simply write R is equal to 2 times under root L by C. Now in this case, both the roots, they're equal, and they're equal to minus alpha. So in this case, I is a function of t, will be C1 plus C2t e to the power minus alpha t. And we have already discussed the initial conditions. That is, when t is 0 positive, I is 0, and L di by dt will be equal to V naught. We should be able to find the value of C1 and C2. And then we'll have our third and practically most important case, which is the case of underdamping. Now in this third case, basically alpha will be less than omega naught, or R will be less than twice under root L by C. And generally C is in microfarad. Unless we have a very high value of resistance, we'll end up getting this underdamping case. Now in this underdamping case, we know that alpha square minus omega square, it is less than 0. Now roots of this equation are lambda equals minus alpha plus minus under root of alpha square minus omega naught square. Now since this quantity is negative, so we can write this as minus alpha plus minus iota under root of omega naught square minus alpha square, and let omega naught square minus alpha square be some omega 1 square. So we can write this lambda as minus alpha plus minus iota omega 1. So in this case, I as a function of t, it will be e to the power minus alpha t C1 cos omega 1 t plus C2 sin omega 1 t, and using initial conditions, again we should be able to find the value of C1 and C2. So for natural response, we have three cases. Overdamping, where the solution is IT is C1 e to the power minus alpha minus under root of alpha square minus omega naught square t plus C2 e to the power minus alpha plus under root of alpha square minus omega naught square t. Second case was critical damping, in which IT is of the form C1 plus TC2 e to the power minus alpha t, and this third one is IT is e to the power minus alpha t, and this is C1 cos omega 1 t plus C2 sin omega 1 t. Now if you look at all the three cases, then it's only in this third case we have oscillations. So here we have damped oscillations, And in graphs, we already know how to draw the graph of e to the power minus x, cos x or sin x. So we'll draw this envelope of e to the power minus x. And then depending on the values of C1 and C2, this graph, it may start from anywhere. So this current, it is going to oscillate, and its amplitude, it is going to decrease exponentially based on this damping factor e to the power minus alpha t. In case of over damping, depending on the values of C1, C2 and alpha omega, you may have different graphs. It could be this graph decreasing exponentially and sharply, or it could be this value first increases and then it goes down, or it could be this value. Depending on the different values of the constants and alpha and omega, you may have different cases, but in all the cases it is quite clear that there is no oscillation. Now basically this critical damping, it is the boundary between over damping and damped oscillations. So its graph, it will look like the graph of over damping, but then in case of critical damping, the system reaches the equilibrium condition or the steady state quickly. So in over damping, the system is going to return to equilibrium or to the steady state without oscillating, but more slowly than in the critically damped case. Now basically critical damping, it is a boundary between oscillatory and non-oscillatory system. And critical damping is the case in which the system returns to its equilibrium position as quickly as possible without oscillating. Now let us take up an example. Suppose we have this RLC circuit where R is 2 ohm, L is suppose 1 Henry and capacitance is 0.2 farad, and initial voltage across the capacitor, it is suppose 20 volts. Now we can write this differential equation. We know L d square I by dt square plus R di by dt plus I by C equals 0, or d square I by dt square plus R by L di by dt plus I upon LC equals to 0. Now we have taken alpha as R upon 2L and omega naught as 1 upon under root LC. Now in this case, alpha is 1 and omega naught will be 1 upon C is 1 by 5. Will be under root 5. So in this case, alpha is less than omega naught. So basically, it's a case of underdamping. So this characteristic equation will be lambda square plus 2 lambda plus 5 equals to 0, or lambda plus 1 whole square plus 4 equals to 0, or lambda is minus 1 plus minus 2 iota. So we can simply write IT will be e to the power minus t a cos 2t plus b sin 2t. So the current in this circuit will be e to the power minus t a cos 2t plus b sin 2t. Now we need to find the values of a and b. Now we know that when t is 0 positive, I is 0. So if we put I as 0, it will be 0. This is 1. This is A. So basically we'll have A equals 0. And if A equals 0, basically this I, it will be B e to the power minus t sine 2t. Now we know that at t equals 0 positive, voltage across inductor, it is 20 volts, and this is L di by dt. Now L is 1, so basically 1 into di by dt at t equals 0, so it will be this B e to the power minus t cos 2t into 2 plus sine 2t and then minus e to the power minus t, and this is equal to 20. Now if we put t as 0, the sine part will be 0, so we'll get 2b equals 20, or simply b is 10. So current in the circuit will be given by this equation 10 e to the power minus t sine 2t, and from graph we know this is the graph of e to the power minus x. Now this is plus 10, this is minus 10, and we need sine 2t. So this is how current is going to oscillate in this circuit. Now in the question they may ask you to find voltage across capacitor, inductor and resistor. Now we know that for a resistor, V is simply IR. So in this case, it will be simply I into R, and resistance is 2 units. So there will be 20 e to the power minus t sine 2t. So that's the voltage across resistor. Now voltage across inductor will be L di by dt. Now L is 1, and if we differentiate this, we'll get this as 10. This is 2 e to the power minus t cos 2t, and then derivative of exponential function minus e to the power minus t sine 2t. So it will be this 10 e to the power minus t, and this is 2 cos 2t minus sine 2t. And finally, if we had to find voltage across capacitor, we know that voltage across capacitor is given by 1 by C and Q. Q is basically I dt, and here we'll take minus I because direction of I is reversed relative to voltage across capacitor. So we are taking minus I. Now this is 1 by C is 5, and this is minus, and I is 10 e to the power minus t sine 2t dt. Now we can write this YCT as minus 50, and then this integral, which is pretty standard integral, so it will be this plus 50 e to the power minus t sine 2t plus 2 cos 2t whole divided by 5. So it will be this 10 plus integration constant c. Now we know that at t equals to 0, voltage across capacitor is 20 units. So from here we'll get this C as 0. So voltage across capacitor at any time t will be given by 10 e to the power minus t sine 2t plus 2 cos 2t. Now we'll consider the second case when we have RLC circuit applied to a DC source. Now here we have this RLC circuit which is connected to a DC source whose EMF is V0. At t equals 0 negative, the switch is open, so there is no current, no charge, and at t equals to 0, the switch is closed. The current is going to flow in the circuit. Using Kirchhoff's law, we can write L di by dt plus Ri plus Q by C, and this is equal to V0. Now we differentiate this. You can write L d square I by dt square plus R di by dt plus I upon C, it is equal to 0, which we can write as I double dash plus R by L I dash plus I upon L C equals to 0. Again, we can write R upon 2L as alpha, which is damping coefficient, and 1 upon LC as omega naught square, which is resonant frequency. So we can write this equation as I double dash plus alpha I dash plus omega naught square equals to 0. And again, we end up getting the same characteristic equation, lambda square plus alpha lambda plus omega naught square equals to 0. Or we can write lambda as minus alpha plus minus under root of alpha square minus omega naught square. So the result is exactly same which we have studied in the previous case. So here also we'll have three conditions. First is condition of overdamping. When alpha is greater than omega naught, that is when R is greater than twice under root L by C, and here we know this I as a function of t will be this C1 e to the power minus lambda 1t plus C2 e to the power minus lambda 2t, where minus lambda 1 and minus lambda 2 are two distinct roots of this equation. Second case is case of critical damping. Now in this case, R is twice under root L by C. Here this IT will be of the form C1 plus TC2 e to the power minus alpha, and then third case is also similar, which is case of underdamping. Now in case of underdamping, this I is a function of t will be e to the power minus alpha t, and then will be a cos omega 1t plus b sin omega 1t, where omega 1 square is omega square minus alpha square. So all the three cases, they are same, they have same implications, they have same characteristics. So we have already studied it. What we'll though discuss is its initial conditions. So we know that when t is 0 negative, I is 0 and di by dt is 0, and when switch is turned on, still there will be no current, so still we'll have I equals 0, and since there is no charge, there is no voltage across capacitor or resistor, so all the voltage it'll go across this inductor. So we'll have L di by dt will be equal to V naught, which is similar to the previous case. Let us take up an example. Now here we are given an RLC circuit connected to a DC voltage source. At t equals 0, voltage is 0, and at t positive, it will give us a constant voltage of 5 volts. We are given that L is 1 mH and C is 1 microfarad. The first question is, show that the condition for critically damped responses R equals 63.2. Now we know that for critically damped response, alpha must be equal to omega naught. So basically, R, it is equal to twice under root L by C. So this R will be 2 times. Now L is 10 to the power minus 3 and C is 10 to the power minus 6. So there will be 20 under root 10, and root 10 is 3 point something, and this value is nearly 63.2 ohm. So for this circuit to have a critically damped response, value of R should be 63.2 ohm. Now the second part is, if we take R as 20 ohm, then derive expression for IT VLT for t greater than 0, and it is given that VC 0 negative is 0 and IL 0 negative is 0. Now in this case, R is 20, L is 10 to the power minus 3 Henry, and C is 10 to the power minus 6 farad. Now here alpha is R upon 2L. Now R upon 2L is 20 divided by 2 divided by 10 to the power minus 3. So there will be 10,000, and omega naught square, it is equal to 1 upon LC, which is 10 to the power minus 9. So it will be 10 to the power 9. Now here lambda will be minus alpha. So minus 10,000 plus minus under root of alpha square. So there will be 10 to the power 8 minus 10 to the power 9. And clearly this is negative value. So it will be this minus 10,000 plus minus. We'll take 10 to the power 8 out. So there will be 10,000. And this is under root of minus 9. So this lambda will be minus 10,000 1 plus minus 3 iota. So basically, I as a function of t will be e to the power minus 10,000 t a cos 30,000 t plus b sin 30,000 t. So that is the expression for IT. Now we need to find the value of A and B. Now we know that at t equals 0 positive, I is 0, and if we put I as 0, this is 1, this is A. So basically we'll get A equals 0. So here I will be e to the power minus 10,000 t b sin 30,000 t. Now we also know at t equals 0 positive, L di by dt, it is equal to V naught, which in this case is 5 volts. So this V naught, which is 5, will be equal to L, which is 10 to the power minus 3 di by dt at t equals 0. So it will be this 10 to the power minus 3, this is B, and then this is e to the power minus 10,000 t. Now this is 30,000 cos 30,000 t, and then minus 10,000 e to the power minus 10,000 t sine 30,000 t. Now we have to find this value at t equals 0. At t equals to 0, this expression will be 0. So there will be simply 30b. So 30b equals 5. So value of b is 1 by 6. So current as a function of time will be simply 1 by 6 e to the power minus 10,000 t sine 30,000 t, and that's our first result. Now we'll find voltage across resistor, inductor and capacitor. Now VR is pretty simple. VR as a function of time is simply IR, and value of resistance in this case is 20. So there will be 20 by 6. So it is 10 by 3 e to the power minus 10,000 t sine 30,000 t, and that's our second result. Now voltage across inductor will be L di by dt. Now L is 10 to the power minus 3 and this is 1 by 6. If we differentiate this, we'll get e to the power minus 10,000 t, and this is 30,000 cos 30,000 t, and then minus 10,000 e to the power minus 10,000 t sine 30,000 t. Now here we'll take e to the power minus 10,000 t and 10,000 common. So it will be simply 10 by 6, which is 5 by 3. So it will be this 5 by 3 e to the power minus 10,000 t, and this is 3 cos 30,000 t minus sine 30,000 t, and that's our third result. And finally we'll find voltage across capacitor at time t. Now this is given by, now we know that at t equals to 0 there is no charge or no voltage across capacitor. So we'll simply write this integral from 0 to t. So it will be this 1 by c, and c is 1 microfarad. So there will be 10 to the power 6, and then this integral from 0 to t, I is 1 by 6, and this is e to the power minus 10,000 t sine 30,000 t dt. Now this is 10 to the power 6 upon 6, and this is 1 upon a square plus b square. So there will be 10 to the power 4 square plus 3 into 10 to the power 4 square, and then e to the power ax. So there will be e to the power minus 10,000 t. We'll have this minus sign, and it will be 10,000 sine 30,000 t plus 30,000 cos 30,000 t from 0 to t. Now this is 10 to the power 10, and here it is 10 to the power 8. So there will be 100 upon 6, and here it is 9 plus 1 10. So it will be 10 by 6, and then we have this minus sign, so we'll change the limits. So we'll put 0 first. So this is 0, sign is 0. We'll get this as 3 and then minus, and then we'll put TST, so it'll be e to the power minus 10,000 t, and this is sine 30,000 t plus 3 cos 30,000 t, which is 5 by 3 times 3 minus e to the power minus 10,000 t sine 30,000 t plus 3 cos 30,000 t, and that is the voltage across capacitor. And if we plot the graph of voltage across a resistor, capacitor and inductor, then this red graph, this is voltage across resistor. This blue graph, it is voltage across inductor, and this green graph, it is voltage across capacitor. So this is how we solve problem of RLC circuit with a DC source.